By the way, we only have some web work due and also 3 writing project due. So I make them all due next Saturday. So do it at your own pace. For some of them, I think you can do all of them already. One of them requires Laplace transform, but I think you have all the tools you need. Okay, so do it at your own pace. Okay, we were talking about Laplace transform, which is given by this form. Whatever, it doesn't really matter. But this one has a really nice property. That is, when you see a derivative, which is usually what we deal with when we have differential equations, you can actually shift it to this thing. So from now on, any derivative, the derivative will be gone. Instead, you will have some Ly. And then you solve the whole equation by algebra. You have Ly equals the sum function of S. And finally, you just do an inverse Laplace transform. You will find what the solution is. That's our idea. We use it for several examples, and now we are actually going into the, discontinuous function, which is something like this. Okay. This is called an activation function, or Heaviside. Heaviside function. So basically what you see here is some function which is 0 for a period of time, and then start to have a value right after a certain time, A. Okay, piecewise defined. And like we said, this can reflect to some rocket, right? You have rocket just fly for like, I don't know, half an hour, and suddenly the first level drop, the third level actually drop, the second level got activated. So you're going to follow a totally different dynamic, a totally different differential equation. Okay, so activation or Heaviside function is actually used for those kind of situations. Then we talk about how to solve this differential equation. We had an example with the activation function. So y prime equals negative y plus u3t. y0 equals 2. From here, you can see this one is basically equivalent to 2 systems. The first one is going to be y prime equals negative y, and the y0 equals 2. This one works for everything up to t less than 3, and for t bigger than 3, you are going to have this. Because now u3 is not 0 anymore, and you need an initial value, which we don't know what it is, unless you solve the first one. Okay, so if you really want to do it, what you need to do is you need to go ahead and solve this. After you finish that, you find y3. After you find y3, you put it here. And then you solve the second differential equation using the y3 you just solved as an initial value for the second part. Okay. That's basically how we work this out in general. And you can imagine for a rocket with 3 levels, you are going to have 4 differential equations. Okay, and you have to solve them in order. The first one, so plug it in. You solve the second one, put the end to be the initial for the third one, and keep going. Now, of course, with Laplace transform, we want to solve them all together. We don't have to do them by pieces. Okay. And this is a classic example you can see, right? It's basically like you have some kind of force. It's activated at t equals 3. Before that, the force is not there. After that, you have a constant force. All right. So that's what we have here. And we try to use Laplace transform. Negative. Actually, let's put this here. And then we already see the power of this. Number 1, you don't have derivative anymore. Minus y0. y0 is nothing but 2. By linear property, you have negative. You can put negative out. You can split them into this and that. I forgot to do this. We did this also. We know the Laplace transform of uat is going to be e to the sa divided by s. Okay, so what we can do is we can do the Laplace transform for this one. Now everything is back to what we have. So we have s plus 1 Ly equals e to the negative 3s divided by s plus a 2. Okay. Therefore, we have Ly equals the whole thing divided by s plus 1. Let's switch the order to take this one at first because it's easier. Okay. To solve this one, we basically just need a way to do the Laplace inverse transform to find y. And we have two terms. We better do them one by one. I would say the first part is pretty easy. This is e to the negative t times a 2. The reason is because we know the Laplace transform of e to the at is going to be 1 over s plus a. Then what we have here for s plus 1, 2, first we change this to 1 by multiplying by 2. Second, plus 1 means, where is it? This is all right. It should be minus somewhere. This should be minus. Okay, so if you have plus 1, that means a negative 1. So we have everything here for the first part. Okay. Now, of course, we need the second part. What is L inverse? Actually, let's just don't do this. Let's just do this. Okay. We have done this multiple times before. You see some complicated denominator, you do partial fractions. So you first take this out. 1 over s plus 1. Second, you notice this is nothing but a partial fraction. So let me do this. I skipped the steps, but you know how to do it. Which gave you this. All right. Now to do the L inverse for the whole thing, it's the same as do L inverse of this and L inverse of this. This is easy because we've already done it. Which is exactly the Heaviside function. So the only thing left, which is complicated, come from here. How do you do the inverse transform of this one? Okay, let's take a look. I will write down several facts. We know this. Okay. We know this. UAT equals e to the negative as divided by s. We know this one because we did it ourselves. We know these two by Laplace transform. Integration by parts, all the stuff. We just did this one in this section. So all these three things I just write down, they're true. Now we have something like this. What is this? It is 1 over s plus 1, which is something we know. This one goes to e to the negative t, right? Okay. Times another term, e to the negative 3s. And if I write down everything in this format, you can see this one has e to the negative as. This one has e to the negative as. So somehow the relation between these two should be similar to the relation of these two. Of course, this is just a guess. This is not accurate, but this is a reasonable guess. Everybody see that? Okay. Then the relation between these two will be similar to the relation to these two. How did we do this too? Well, the first one is this. Okay. E to the negative st dt. That's how we got 1 over s. The second one, what did we do? We did this. Okay. Now, if you just keep going, how did we get this again? Well, technically, we did negative 1 over t. No, 1 over s. We have a b here. We have a 0 here. We have a limit. B goes to infinity. Okay, which give you, if you pick the thing to be right, 0 minus 1 over s minus e to the s times 0. Okay, finally, if you finish, this is 1 over s. Why? Because this part goes to 1. Okay. What will change if I replace your 1 to be this uat? Number 1, it won't change much. Number 2, what are you going to do? Let's do the same thing. Number 1, this one goes from 0 to a, 0 e to the negative st, which is basically not there. Then uat becomes nothing but 1. So can you see what a uat does to our original function? It simply changed this ending point from 0 to infinity to from a to infinity. Why? Because before a, the whole thing is 0. After a, you don't change a thing. Good so far? That means what? That means if you do the integration, you still have the same thing. Except before you put 0 here, because your ending point is 0, now you put an a here. Okay, which give you 1 over s times e to the negative sa. Make sense so far? Okay, so where does this term come from? It actually comes from e to the negative s0, except before you put 0, now you put a. Why do you change the starting point? Because you multiply by a ua. That's basically delay. That's basically shifted the whole function to the right by a. So if I write it down, now you can see what is this? What does it do? It basically gives you the same thing, except before you have 0 to infinity, now you have from a to infinity. Okay. e to the negative st. Okay, it shifted the whole function to the right by this much. Therefore, I think we can write down the general format. So now, that's number 2. Shifting a function. And the answer is quite easy. Let GAT equals UAT FT minus A. Okay. Then LG AT equals e to the negative SA L FT. Okay. That's the hint. Basically, what you did is you did this. Okay. Now you shift it to by applying a UA. Okay, but finally you want to shift everything back because you still want everything to start from 0 to infinity in order to get alpha. So what you do is just do this. Which give you then the whole thing here will just multiply by e to the negative SA because your ending point is still there. Once you shift that, you still have a leftover. That is e to the negative SA. Is the idea clear? You take the first function, you shift to the right, okay, which start from A now, not from 0, but you wanted to start from 0, so you shift everything back. But when you shift it back, you need to multiply by the constant. That's the logic. Okay, of course, to have something more concrete, we can simply just prove it. Let's just do LGA. Let's prove it. So what's this? Well, it's going to be okay, which is going to be because before A, this one is 0. Okay, so only this. Now, if that's the case, I take a U sub, I let U equals T minus A. This will become from 0 to infinity FU e to the negative S, okay, U plus A. D U, because dt equals du. So I shift everything back. Which is this. Okay. times e to the negative SA. Notice, what I did is basically I take this one, I decompose it into two terms. One is here, one is there. This one is the integration with respect to the u. That means s and a are both constant. If it's a constant, you can take it out. And of course, this one gives you e to the negative SA times LF. So that's the proof. The idea is just shift right, shift it to the left. There are some details. I included all the details here. All right. So that's the formula we're looking for. Thinking process is in this dashed box, but now we have the tool. Let's write it down. Okay. We were looking for this. What do we know? We know this. So if we let ft equals e to the negative t, okay, then LF is going to be 1 over s plus 1. Then the function we're looking for, let's name it g. Then LG is nothing but e to the negative 3s times LF. Like we just said, if you put this one, then g will be nothing but u3t ft minus a. This comes from the fact. Okay, this is the fact we just proved. A shift. Okay, now u3, you already know what it is. ft minus 3, that's going to be e to the negative t. But now, instead of t, you do t minus 3. This will be the function we're looking for the last part. Okay. So let me wrap everything up from, or should I, let's just redo it. Okay, since it's already here. We started from here. All right. We did this. S Ly minus y0, which is 2, equals negative Ly plus e to the negative as. A is 3. Okay. We did this. We divided by s plus 1. After that, we split them into this term, and this term using partial fraction. Before we get stuck here, now we realize this is 1 over s. This is 1 over s plus 1. This one goes to e to the t. No, this one goes to 1. Sorry. This one goes to e to the negative t. The only difference is I multiplied each one by e to the negative st. No, negative 3s. That's the only difference. Now, by the formula we just calculated, that just means shifting everything to the right by a. So we can say y equals 2 from here, okay, plus u3t, okay, minus e to the negative t minus a times uat by what we just finished here. In this way, we solve the two differential equations in one step. And of course, your answer actually depends on where you are. Okay. If you think about it, this basically means when t is less than 3, the answer is this, because both are 0. When t is bigger than 3, you have the answer like this. That's basically what you have. Okay. Take some time to read this. Okay. Does everything make sense? Laplace transform should be okay. I think everything up to here should be number 1, okay. The hard part is how to do the inverse transform. For now, we only know a few. We know e to the st, at, that's one type. Now I know another type. Plus, if you already know something like 1 over s plus 5, this one goes to e to the negative 5t. Then multiply this one by e to the negative 2t, simply give you something similar, except shift it to the right by 2. That's what activation function does. Sounds good? Okay. So from now on, if you see the same Laplace transform but shifted to the right, you will totally know. Okay. That is the same as times this one after the Laplace transform. I think the only thing maybe a little bit confusing for now is just try to get familiar with how to do this. So I will just write down several examples so you can see the pattern. 1 over s plus 4. If you do the inverse transform, it goes to e to the negative 14. Okay. But what if you multiply this one by a e to the negative 2t? Then this one gives you the same thing, except with a u2 t come from this 2. Okay. E to the negative 4 t minus 2. Exactly the same thing, except for this one changed to this. And you multiply a u2t at the beginning. Okay. That also means multiplying this one on a Laplace transform physically means delay by a, because you shift everything to the right by a. Okay. So you have a delayed differential equation. Of course, you have a delayed solution. Okay. You won't activate the force on 2 times 3. Then you won't have the effect of the force, which is this part, onto 3. It's the same thing. Then from now on, you can write systems, especially multi-level systems. From time 1 to the first hour, you have some dynamics. From the first to second hour, you added some additional dynamics. From the second to the third level, you add another additional, and maybe you delete some of the dynamics before. Now everything can be done using this heavy-sided function. So you can write multiple processes into just one equation. Okay? You don't have to do piecewise defined function anymore. The good news is you can even solve them together. You don't have to solve them separately. Okay? And that is very convenient in real applications. All right. That will be everything for the first discontinuous function we introduce, which is called the heavy-side function. You may have some other cases. Each one has some meanings in physics. Okay, but this one I think is very popular because basically anything which is a jump, you can use this UA to define it. Okay, for example, something jump from 3 to 4, you can simply use UA t plus 3. And no, you just do 3 plus UAT. So you can actually easily to say something jump from 3 to 4 starting from time 5. Then you just put a 5 here. So any jump actually can be characterized by this heavy-side function. All right. Any question before we move on? Is the idea here clear? Okay, do some practice. You just need to get used to this formula. And you already know what it means. It's just to compute it in the right way. There are two things you need to be careful of. The shift as well as the activation. Yeah, that will be good enough. 6.3. second order differential equations. Well, of course, we have done second order before. We know this comes from the harmonic oscillator part of it. We have the undamped oscillation, damped oscillation, overdamped, underdamped. We have all the cases. Okay, so we already know how to do this, but this time we want to do it with Laplace transform. That's number one. Number two, everything we have done before, we'll assume the homogeneous case. If you remember, we assumed this y prime equals ay when you change everything into a vector, right? But we never did a case where we have force applied to the equation. For example, cosine, 3 cosine 4t. We have never done a case like this before, which is not homogeneous. We can't do it from 0 to external force. Now with Laplace transform, this time we can do it. Okay, that's basically the whole idea of this. So let's redo what we know before, make sure it satisfies what we had before, and then let's go ahead and try to do the new case. Okay. Of course. We know the solution, right? The solution involves e to the at and sine and cosine omega t. If you solve this, you will definitely get one of these, okay? If it's just e to the t, we already know how to do it, right? Laplace transform of e to the t, at, we know it's gonna go to this. Now the problem is, we never had done anything like this before. We don't know the Laplace transform of sine omega t. But in order to do second order, you would definitely see sine and cosine somewhere. Actually, not definitely, most of the time. Okay, you will see sine and cosine somewhere. So the first thing we want to handle is probably we want to know, what is this? What's the Laplace transform for sine? And what's the Laplace transform for cosine? Because if we solve the system, we're definitely going to see it. First choice, you can do this. Do you remember how to do this? The easy one. Let's just consider 1 and 1. Do you remember in calculus 2, you need to do integration by parts? And then you need to do integration by parts again. Okay, you have two of them, you divide it by 2 in the end. So it's going to be doable. Okay, integration by parts. I don't want to spend time in class doing this. So you can go online and try to see how to do it. It's pretty, I won't say easy, but straightforward. For twice. You will be able to do it. Okay. Then you are going to have some hard to handle ending points because this time you have 0 and infinity. So just be careful. So that's certainly one way to do it. It's just not easy. So what we instead want to do is we want to solve it in an alternative way. That is this. Okay. We know sine omega t is the solution of this dφ. right? You take the derivative of twice, you basically got omega square and yourself. Plus y0 equals 0. For second order, you need another initial condition, that is y prime 0. And what is y prime 0? Well, if you already know y equals this, y prime is nothing but omega cosine omega t. Y prime 0 is nothing but omega. Okay. So sine omega t is a solution of this. That means if you Laplace transform the whole thing here, you should have the Laplace transform of sine omega t. Let's go ahead and do it. Step 1. Good. Let's move it to the other side. Actually, I don't have to. Either way, I need to extend it. Okay, so let's don't worry about it. Okay. Double prime. This is what we know. That means this one, according to this formula, equals that minus y prime 0. If you treat your y prime as your original y. Right? You take away a derivative, you put an s here, you minus the 0 value of the thing inside. Except this time it's not the y prime, it's y prime then prime. So the whole y prime is almost like the y before. Okay? Omega is a constant, so take it out. And you know this is omega according to your setup. Okay. Now you have another L prime, Ly prime. So do it again. Just for this part, which goes to this. Okay. And you know y0. That's how you did it. It's 0. So s square Ly minus omega plus omega square Ly equals 0. This tells you Ly equals omega s square plus omega square. All right. If y satisfies this initial value problem, then Ly equals this, according to the property of Laplace transform. Second, sine omega t is the only function that satisfies this initial value problem. Therefore, this y has to be sine omega t. Then this is the Laplace transform of sine omega. Which is way better than integration by parts for twice and handling infinities. Sounds good? Okay. We constructed an initial value problem that only sine omega t will satisfy. Then we try to pretend we don't know it. We use Laplace transform to solve this one. We find the only y that satisfies this initial value problem will give us a Laplace transform which looks like this. In addition, sine omega t is the only function that satisfies this. Therefore, this will be the Laplace transform of sine omega t. Okay. The tricky part is how to do the Laplace transform of y prime prime. Because we only know how to take away one of the derivatives. Then you just do it. Y prime prime, you take away one derivative, you have this. Okay. Then do the Laplace transform for this part again. You will have something else. Sounds good? What about this? Prime prime prime. Well, that's going to be S L y prime prime minus y prime prime 0. Good so far? S L y prime minus y prime 0 minus y prime prime 0. Okay. Then S minus Sounds good? So what's going to happen? Well, if it's a third derivative, you are going to have a S, and a S. So finally, all the derivative is gone. You are going to have an S cube somewhere. Okay? Second derivative is going to give you S squared. First derivative is going to give you S. Okay. Fourth derivative give you S to the fourth, whatever. Okay. You are going to have some leftovers. But they should be all given by the initial value problem, so they're just numbers. Right? If you know the third derivative, you need to know y0, y prime 0, and y prime prime 0. These should be initial values. Sounds okay? All right. Then, even though we're doing second order, now you probably start to realize a simple fact. That is, what if you have something like this? Well, it looks pretty complicated. Okay? However, let's do L. What's going to happen? This one will give you S to the fourth. This one is going to give you 3s to the cube. This one is going to give you 2s squared. This one is going to be negative 6. Every single one has a Ly. Okay. On the other side, you are going to have some Laplace transform of this thing, whatever that is. Sounds good? You will have some y0, y prime 0, y prime prime 0, but like we said, they're just constant. For initial value problem, you should already know it. So on the left, for everything here, what you will see is nothing but a polynomial of s equal something. So what's the solution finally? It's going to be Ly equals something, whatever that thing is. Okay, divided by a polynomial of s. Make sense so far? Okay, so your Ly will always be something look like a rational. And how do you solve for the rational when you take the inverse transform? Whatever you have here, okay? Looks familiar? Partial fraction. Okay, that go back to calculus 2. Now what happens for calculus 2? Number one, if you do partial fraction, you will only have two kind of factors. You will either have a linear or you will have an irreducible quadratic. Make sense so far? For linear, it goes to this, period. For irreducible quadratic, now look at sine, cosine. What's this? This is irreducible quadratic. Okay, so everything got connected. Every time you do a Laplace transform, assuming everything is easy, okay, you end up with a rational function, rational type of function, quote unquote. Then you can do partial fractions, and when you do partial fraction, you only have two kind of denominators, the linear ones and the irreducible quadratic. The linear ones are always corresponding to exponential, and the irreducible quadratic is always corresponding to sine, cosine. Okay, and the top really depends on what kind of force you put initially. Okay, from here you can see Laplace transform can always handle things like this. And when I say things like this, I say something which is linear with constant coefficient. Okay, if it's not linear, it's going to be not possible. And if it's linear, but the coefficients are not constant, sometimes it's doable, sometimes it's not. It really depends on the Laplace transform of the thing. So that's a powerful law. All right. Does everything make sense here for this sine thing? Can I do the same thing for cosine? You just need to construct an initial value problem. Same thing. Y prime prime plus omega square y equals 0. But this time, your y0 is not going to be 0 anymore because you are having this. So y0 is 1. Y prime 0 is going to be 0 because whatever omega, it doesn't really matter. You have this one. Okay. Use Laplace transform to do it. You should end up with Ly equals something. That something is going to be the Laplace transform of cosine. Okay? Try it by yourself, and we will give you the answer next time. So you're looking for this. That will be the Laplace transform of cosine. Okay, that will be all for today.